In this video, we're going to be talking about functions and what happens when we do some transformations to them. So I want to skip this first page for a sec. We'll come back to it. It really won't make sense until we see some examples first anyways. So we're going to jump right into some examples here. What does it look like when we transform or move a function or change it in some way? Either we change the shape or we change the location of it. With linear functions, a little bit more basic than the other functions we're going to see in the other examples, but we could talk about it to begin with. For the most part, we're familiar with linear functions in that the value in front of the x coordinate is going to be our slope, and this constant number that is written at the end in slope-intercept form is going to be our y-intercept. But as it turns out, those are actual transformations that apply to other functions similarly, but slightly different. It just depends on the function. So if I have a parent function of a linear function, just y equals x, or f of x equals x, I know that that has a y-intercept of 0 and a slope of 1. So we can sketch that in there. What happens if I add that y-intercept, or that constant, out to the side of it? Well, it just shifts the function up or down, depending on whether that value is positive or negative. So since we have a positive 2 as our vertical shift value, then we're going to shift up from where the original graph was. If you need to, sometimes we don't necessarily know how to draw the graph, so we could fill in a data table to do that. So if I plug negative 2 into this function, I get 0 out. So I know that negative 2 comma 0 is a point on our graph right here. And we can fill in the rest of that table, plot those points, and then connect it to draw the graph. Although hopefully we already know how to draw a linear function. So having the parent function and the newly transformed function, let's describe the difference between those, trying to use the vocab of transformations. A shift is sometimes called a translation. If it's a positive value, we move up. If it's a negative value, we move down. So this was a positive shift up 2 units, or a vertical shift of positive 2. Let's get a little bit more complicated on this next one. This is an absolute value function. Its parent function, or most basic form, is just the square root of x. And if you don't know already, that's just a v shape. It's kind of like a linear function, except broken here at the origin and reflected across the y-axis. It still has a slope of 1, but otherwise it's very similar to that linear function. So we got this original v touching the origin. Call that the vertex. Here we have the generic transformed version of it. What we're going to find out is that if I add 1 to my x value and take the absolute value of that, if I make this a value negative 1, we're going to see what that does. And if we add a constant out here for that k value of 3, we'll see what that does. So you could fill in your data table. If I plug a negative 2 in here, negative 2 plus 1 is negative 1. The absolute value of that is 1. Make it the opposite. It's negative 1 plus 3. So we get 2. So negative 2, 2 should be a point on my graph right there. Plugging in negative 1, we get 0 here. So negative 1, 3 should also be a point on our graph. There it is. That actually turns into the vertex. Plugging in the rest of the values, you should see how you finish off the graph. But we don't need this table. If we know how to graph this parent function, let's just look at these transformations that are occurring. The h value is going to be a horizontal shift, and it's always going to be the opposite of what it looks like in its equation. If it says positive 1, we're going to move left 1, because actually what it was x minus negative 1, and so that h value had a negative 1 value. And then the k value is going to do exactly what it looks like. If it's positive, it's going to go up, and if it's negative, it's going to go down. So I'm going left 1, up 3. That's going to be my new vertex. Before we do that, though, notice that our a value is negative 1. If that a value is negative, what it's going to do is it's going to reflect across the x-axis. So this v got reflected upside down first, and then that vertex got shifted left 1 spot, up 3 spots. And so the graph looks the same. It just got reflected and moved. And so knowing that transformation form will let you graph much easier or much faster. So we reflected across the x-axis and we shifted left 1 up 3. Or we have a horizontal shift of -1 and a vertical shift of +3 after a reflection across the x-axis. Let's keep working. We got a few more to go. Here we got some basic polynomials, just a basic quadratic and a basic cube. So once again, we're going to graph the original parent function, x squared. Hopefully you can do that using a quick data table if you need to. And then we'll see what its transformational form does to that graph. Very similar to the form in absolute value, the h is going to be a horizontal shift, this k is going to be a vertical shift, and this a now is going to kind of act like a slope of some kind. I'll give you another way to think about it when we graph it here. So here we have a transformed version of this parent function. So what happened to the original? Well, it got shifted to the right 1. H value is 1. It got moved down 2, and that a value is now a fraction. Let's see what that does to our graph. If we fill out the data table based on that equation, or if we change the form of it, we could simplify that x minus 1 squared, FOIL it out, or expand it. Then we can see it in its expanded form instead, although that doesn't help us with our horizontal shift, but it does help us identify what type of shrink or expansion just occurred. So this is going to be a vertical, because that a value is going to be a vertical shrink or a vertical expansion. It's either going to widen or make the graph skinny. If the a value is a fraction between 0 and 1, like it is here, what it's going to do is it's going to shrink the graph. And what that means is if it's a vertical shrink, I'm pushing down on the graph vertically, which is going to widen our graph. It's a little backwards or counterintuitive to think that way, but if you think of like it's a vertical shrink, meaning I'm pushing down vertically on the graph, which is going to fatten or widen my graph out. So it's becoming wider as a result, and then that vertex is going to be moved right 1 spot, down 2. So right 1, down 2, which is exactly what we get as a result if we were to fill in our data table there. All right, so hopefully you're starting to get the hang of it. You will see this form happen a lot. It looks slightly different with our different functions, but overall it's got many of the same features here, and they act much of the same way. If we have a cube function, its most basic parent function looks like this. It's kind of a disco move. So what we're going to end up doing is take this center point, and that's going to be what gets moved, shifted, or the graph could be flattened or widened, or shrunken and made skinnier. So the a value here in our newly transformed equation, well, we didn't change anything about that, so we're not going to change the shape of the graph at all. All we're going to do is move it. Let's take a look at our horizontal movement. It's going left 2, the opposite of what we see, and up 1. So taking that original graph, taking that center point, moving it left 2 and up 1, just moves all of our points relative to that. You can also check it using the data table. We got 2 more. Let's take a look at what are called root functions, or sometimes called radical functions. Any function that involves a radical symbol around our input. Its most basic form of a square root function looks like this. When we graph it, maybe you could think about plugging values in that are easy to evaluate square roots, such as 0, 1, 4, and 9. Those in-between values are kind of hard to do without using decimal forms. So let's see how that original parent function gets shifted here. We're looking at the transformed version of it now. No shrinking or widening here, but we do have a horizontal movement and a vertical movement. So for square root functions, we take that endpoint. That's what gets shifted here. We're going to shift right 2 spots and up 2 spots. And again, you can use the data table there to verify that. All right, last one, we got a cube root, very similar to the square root. Except this time when we take cube roots, we can have negative outputs, whereas in regular square roots, we can't without imaginary numbers. So let's remember that for cube roots or any odd numbered root, we can have a negative output. I did change the data table here from your notes because it wasn't working for the function very easily. So I gave some new numbers here. You can change that up, let it work a little easier for you. All right, we do have one more new transformation here that we haven't talked about yet. Otherwise, many of the same things that we've been describing before. The original parent cube root function kind of looks like a helicopter or a lawnmower blade. That's the way that I like to think about it. And it's got that center point again, just like the cube function had. That is what's going to get shifted. But let's see what else is happening. We have a negative value in front of our x. Anytime you have a multiple or a number in front of your x there, that's going to end up horizontally shrinking or expanding a function. And that's really difficult to see in a graph. Really the best way to see it is just in its equation form. Well, let's see what it does to our graph here. Plugging in these inputs, you could plot it to see, but we could also just know, based on our transformation form, what's happening. So because of that, we're actually going to reflect, because it's negative value in front of the x is going to reflect it across the x-axis. So this graph is now going to be upside down of what it looks like originally. And then it's going to get shifted right 1 spot and down 5 spots. And so now it's upside down, and that center point got moved down 5. Oops, and I made a mistake. It's actually moving left because that value in front of the x is the opposite sign. And so actually we're going to have to think the opposite of what we just said. So instead of going right 1, we're going left 1. So another way that can make our values really tricky to evaluate. Not commonly happening in our class, so don't worry too much about that. Definitely be used to horizontal vertical shifts and occasionally a vertical shrink or expansion. So there's some basic parent functions and their generic transformed versions. Be able to recognize graphs that get transformed. So if I give you this, be able to tell me what transformation happened. Or if you're able to graph it, be able to use a data table or a graphing utility to sketch it out. All right, let's go back to that first page now where we can really talk about this stuff with some more knowledge here. In general, we always have a parent function, and then to go with that parent function is usually some generic transformational version of it. It won't always look exactly like this. Obviously, we saw ones that don't look exactly like it, but many of them carry the same format, so I just thought I'd give it to you as an example there. The A value is going to be that vertical shrink or vertical expansion. If it's negative, that's going to reflect across the y-axis. If I have a negative in front of my x, that's going to reflect across the x-axis. So here you see two versions of that. And the h value coming next, that would be our horizontal shift. So if I add or subtract something next to my x value, that'll shift it left or right. Be careful, it's always the opposite of what it may look like, or if you think backwards one step and think about the h value, that'll tell you what it's doing. The k value, that constant that's out to the side of it, is going to be your vertical shift, moving up if it's positive, down if it's negative. Those are the rigid transformations there, not changing the shape of the graph, but just changing where it's located or flipping it. The non-rigid transformations are those stretches or shrinkages. That's a weird word. Expansions or contractions is another way of thinking about it. That's where we change the shape of the graph. It gets thinner or wider. If we have that a value in the front that's greater than 1, that's going to make the graph thinner or stretch it vertically. If that a value is a fraction in between 0 and 1, that's going to widen or crunch our graph. And then the most difficult one, I think, to see, especially if you're just looking at the graph, is the horizontal stretch or horizontal shrink. And so that's if you have a multiplier in front of your x. If it's a fraction in between 0 and 1, that's going to stretch it horizontally. And if that multiplier in front of your x is greater than 1, that's going to horizontally shrink it. So you got some examples here where you can compare the graph. I think it's really difficult to tell the difference between these two if you're just looking at the graph, but when you look at it in its equation form, you can see the difference here. We have a multiplier of your total function, or you just have a multiplier in front of your input variable. All right, so there's a little bit of review about transformations and graphing their parent functions or describing how transformation graphs look different.